Welcome to my live workshop where we are going to learn how to control pretty much any DC motor with an Arduino. That way we can start programming some custom movements for our motorized props, our animatronics, our robots, or heck, anything that you're building that needs some very cool movement. I know what a lot of you guys are saying. I don't know how to code. I've never coded anything before. This is going to be way over my head. It is not. Listen, I did it. I kind of tried to stick with ye old motor speed controller. And via this little knob here, you control the speed of the motor. So you set it and forget it and just let it go. But after a while, you're going to find that you're kind of bored at looking at the prop moving that way. Watching the same animation over and over again gets kind of monotonous. And so today we're going to try and figure out how to unmonotonize those movements. Can we just connect the motor to the Arduino? I wish, right? Video over! But no, alas, we can't. The poor little Arduino, its pins right here only put out 5 volts. And well, this requires 12 volts, so it's going to have a tough time running. Not only that, each pin is limited to 40 milliamps maximum. Well, these motors are going to draw way more than that. To power something like this, I always recommend a 12 volt, 5 amp power supply. So there's no way that this Arduino is going to be able to power this. This thing will fry like a lot of my other electronics. It'll join the bunch. So we kind of need a translator, a power translator, if you will. And that's where motor driver modules come in. Sometimes they're called motor control modules. Here is your Arduino, and we're going to write code. And this code will send instructions to our motor module. Now, our motor module can definitely handle current and power and all that. And it's going to translate this to your motor. And whether you're using this motor, we got this little motor right here. This is like my 9 volt right there. And there's even smaller motors. And motor driver modules come in all kinds of shapes and sizes. Mostly, you're going to see them either as a chip. You're going to see them bigger like this. And many of you guys will remember our motorized spider prop project. This is motion activated, and through the nose of the skull, it fires a silly string at you if it detects you. The legs move, and it's also motorized. It'll chase you down the street, and it's in its prototyping stage right now. So it's kind of moving along a little slower than I'd like it to. I hope you guys can relate. If your projects are also not going as fast as you would like, please post in the comments so I know I'm not the only one. So you see this hot message going on right here. And I kind of don't want to give you a close-up, but I'm going to. You can't unsee this. We got a whole bunch of spaghetti. We're just missing the meatballs to go with it. But if you peek over here, you can see these motors. Now, these are 3 to 6 volt motors. And same thing, this is an Arduino Mega. This can't just hook directly up to the motors. So we have our translator here, our motor control module. And this is the L298N. I can't believe I remembered that. And what's the difference? How do you even choose a motor control module for your motor? Mostly, it has to do with the power capabilities of it. That's really what it comes down to. There's other little things, but really that's what you're looking for. Something like this and that L298N cannot handle the amp draw that something like this is going to draw. You're going to need a motor control module that's beefier. So for instance, that motor control module can handle up to 2 amps per channel. Certain motor control modules can only control 1 motor. Some can control 2. This one can control 2. And it can handle 7 amps. So that means it can deliver 7 amps of power to this motor, which is great. And the name of this one is the XY160D. So let's take a closer look at this motor control module, and you're going to notice a bunch of stuff on it, but we're just going to concentrate on the important stuff. So the green terminal connector here is where you hook up the power that is going to power your motor. I have here a 12 volt 8 amp power supply. So that's going to get hooked up right there. And this is the power that the motors, which you can hook up here, are going to use. And this is where you hook up your motor 1. This is where you hook up your motor 2. And there's the screw terminals for positive and negative for each of your motors right there. So that's hooking this up to the motor. Now, hooking this up to the Arduino is on this side. You see a series of pins right here in vertical columns. So this vertical column right here is how we connect motor number 2 to the Arduino. And we're not going to deal with motor number 2 because once you hook up motor 1, motor 2 hooks up the exact same way. Our 5 volt, that's the first pin at the very top. Now this connects to the 5 volt pin of the Arduino here. And that is going to power the board. So we're powering the motor through here, but the board needs power too. It's like, give me a little love too, right? The next pin we have is called ENA, and that's enable A. On the other side, it's also called enable A. Usually on most motor driver controllers, it'll be called ENA and ENB. So enable A and enable B, one for each motor, but this one, it just happens to be called the same thing. So the next one is called IN1, and the one below that is called IN2. These are the pins that are responsible for controlling direction. So your ENA, your enable pin, controls speed. And then finally, we have a ground pin, which is unusual for motor controller boards to have kind of a ground pin that goes directly to the Arduino. Normally, what you have to do is split your ground coming into here and send one to the Arduino, and then one goes to your power supply. This is where you connect to your computer to upload the code to the microcontroller chip right here. The Arduino has a couple ground pins just to make kind of life easy on both sides. Here we have the 5 volt right next to it, and the 5 volt will send 5 volts out to power things. So this is where we are going to power our control module. These pins we're not going to use for today. They're your analog pins. We're going to be working pretty much on this side of the board, and these are your digital pins. I usually don't use 0 and 1 because they're also used for other things, but from 2 to 13, you can use any one of these pins. Now you'll notice some of them have like squigglies. What the heck is that? It means those pins have PWM functionality. Now, each of these pins, all of them, what they do is when you want to turn something on, it'll send 5 volts out. When you want to turn it off, it'll send 0 volts out. But some things like speed are nuanced. They're not either 0 speed or high speed. There's speeds in between, right? And that's what the squiggle helps us do. Well, not exactly the squiggle, but it tells you that this pin not only works as a on-off type of switch, but it also can do the nuances in between. And so for the speed pin, it would make sense connect it to one of the squigglies. The first thing we're going to do is hook up the 5 volt pin to the 5 volt pin of the Arduino. And for that, the easiest way to do that is using these breadboard jumper wires. They're the DuPont style ones. So they come with male ends, male-female ends, and female-female ends. Now, working with motor drivers, primarily you're going to need the female to male ends. And I'm going to find the 5 volt pin of the Arduino and stick it in there. All right, so now the Arduino can power the board so it can do its rigmarole. If you don't have a ground pin, which a lot of times you're not going to have a ground to go to the Arduino, you would basically take a jumper wire, cut off the end, stick it in here, and then stick it in your Arduino. So you have like 2 grounds coming out of here. The ground is actually the last one. We have a ground right next to the 5 volts. So I'm going to go ahead and just kind of keep them together. They can like chat with one another. The second pin was our ENA pin, our enable pin. That's our speed pin. So we want to try and connect the speed pin to one of these pins with the squiggles. So for that, I'm going to use green. Green for go! So we know that's the accelerator pedal right there. So I am just going to try and slip that in. And we can see that number 9 has a squiggle. So I'm going to go number 9 on this. Now we have our 2 directions, so I'll just make them blue. So direction 1, or in 1, which is the 3rd pin down, and see, this is where it starts to get, gotta fit it in here. Our 3rd pin. So in 1, I'm going to put that on number 7. Now for the direction pins, it's okay if you put them on the ones with the squiggles. Doesn't do anything because the squiggles works just like the other ones. They just have a bonus feature. And then I'm going to hook up I'm going to put that into pin 8. The Arduino board is officially hooked up to the motor driver controller. So next, let's just shift this guy here and hook up our motor. If you're hooking up a regular motor, well, it's pretty easy. See how it only has these 2 leads? You know, if it had wires on it, then you would just connect them here. These are labeled out 1 and out 2. And it doesn't matter which way you connect it. It doesn't hurt the motor. It works just fine. You connect it one way, it'll turn counterclockwise. If you connect it the other way, it'll turn counterclockwise. Wiper motors, you're going to find that they have anywhere from 3 to 5 wires. Mine is a 5 wire, so I kind of tape these guys back here because, you know, we're not going to be using them. So the black is my ground and the yellow is my high-speed wire. The green one tucked away in here is the low-speed wire. So I like using the high-speed because it gives you more of a speed range to choose from. If you're also working with a wiper motor and you're like, I don't know what my wires are, I have a in-depth video and tutorial, so hit the link below for that. And once you kind of get your wire situation sorted out, well, heck, you can come on back and pick up where you left off. Put you in here and you in here. Guys, we're almost done. We are going to hook up power to the motor. So this is our 12-volt power source right here. Now for this, I always like to pick up a female adapter. Power ground goes in here. So we have that connected, which means we can connect our motor. But I'm going to hold off on that. In order to upload code to our board, I have my USB cable, which is also plugged into my computer. So I'm going to go ahead and hook him up. And I usually like to work with the other components unhooked for now until we're ready for them. To download this program, it is free, which is like the best thing of all. I love free stuff. Go to the official Arduino website and then you download the type that fits your operating system. So when you fire up a blank sketch, this is kind of like what you get. And I'm just going to take a quick moment here and see that my board is set indeed to the Arduino Uno and the correct port, meaning where is it plugged into your computer? And oftentimes it'll cheat. It'll kind of like tell you like, pick me. You're going to see 2 kind of areas, this void setup area and this void loop area. So anything you put in this setup, the program is going to read one time. And so it's like instructions that you just need to tell it one time. And it's like, okay, I got it. And in the void loop area is where you put the code that gets executed over and over again. So whether you have 1 line of code in here or 20 lines of code, it basically reads it down in order, one by one, executing it. Once it gets to the last line, it goes back up to the top within that section and it starts it all over again. So the first thing we need to do is tell the Arduino what pins we're using. Just because you connected it to the physical board, it's not like auto sensing, like, oh my God, I got stuff hooked up to me. We're going to give them our own names. So the first pin, let's start with the direction pins. So in 1, and I set that to pin number 8. The int that you see here stands for integer, and you can see that it just kind of turned into a color. Arduino has certain keywords that it recognizes that it's like, oh, I know what you're talking about. So an integer is any whole number, or pins are whole numbers, 1, 2, 5. There's no pin 2.5. We're telling the Arduino that we have our in 1 from the motor connected to pin 8. Now this name here, you could tell doesn't turn any color. You can make this up. You can call the in 1 pin cats, cats rule pin. But the problem is when you come back months later, you're not going to remember what cats rule is. So you always want to make it like very descriptive. Let's do the in 2 pin. I'm going to call it in 2 pin. And that was connected to 7. And then let's do the enable pin. The enable pin is connected to pin 9 with the squiggly. And you never want spaces in your made up names. It's all got to be squished together, and capitalization matters. So anytime you refer to this later on in the code, you have to make sure you use the exact same capitalization, spacing, everything. I usually like to name it what it's labeled on the drive because for troubleshooting, it just helps me find it a lot faster, but that's up to you. For the void setup, each of those pins can be used as an output or an input in the Arduino board. So you kind of need to tell it how you want it to behave. What mode is it going to be in? Is it going to be in an output mode or an input mode? Well, because the Arduino is going to be outputting information to the motor driver, they're all going to be output modes. We're going to set the pin mode, and you can see it turn to color. It's like, oh, I recognize that. The pin mode of what pin? Well, the in1 pin. Let's start with that one. So we want to set the mode of the in1 pin to an output, and you can see it recognizes that. You can also set, if you're working with a sensor or a button or something like that, you can set it to an input. So you can see it recognize that. And again, capitalization matters. If you use other capitals or lowercase, it's not going to turn colors on you. And you want your code to look all Bob Ross. That's when you know you're doing it right. So let's do the next one. And that's also going to be an output. For the next one, our speed pin, well, that's definitely an output because we're going to be outputting some speed. Yes, we are. So let's set that to an output. So far, we've pretty much completed our setup for this. We've identified what pins are what using variables. So this variable right here will store the number 8. So when it reads it here, it's like, oh, what's in one pin? Oh, it's equal to number 8. So that's a much easier way to do it. Now, alternatively, you can just put actual physical pin numbers in here. The problem with that is inevitably your projects are going to start getting bigger and bigger. And every year or every couple of months, I always like to go back to my project and expand upon it. Hence all of my unfinished projects. I should probably stop doing that. When you use a variable, say you add on to your project and you got to jump this to another pin, it is so much easier being able to change it up here. Like say this needs to move to pin 10. You put pin 10 in here. Every time in one pin comes up, it's going to be like, oh, it's pin 10. Okay. So you can house all of your pins and have one place where you make all your changes instead of having to go through all of your code. This might end up being 100 lines of code by the time we're done. But it's not. Let's move on to the loop section, which is a section that gets executed over and over again. In this first example, why don't we just get the thing to move? We want to send a signal to either in1 or in2, not both, because if you send a signal to both, they're going to try and move in different directions at the same time. And that kind of doesn't work. In order to send this signal out, we use a function called digital write. And you can see, just like pin mode, it's like, I know what you're talking about. The values you put in here is your pin number and what you want it to do. Like if you wanted to send a signal or not send a signal. We want to write the in1 pin, which is pin 8, high. So when you write something high, it means that it's going to send 5 volts out to the motor driver pin. The motor driver is going to take this 5 volts, then it takes the power from the power supply and juices up that motor to turn it the way you want it to turn. It's also good measure that if you are sending a high signal to in1 pin, you also want to tell it, like, obviously, then don't send a signal to in2. So that way it only turns in the one direction. And when you set this to low, it means 0 volts are sent out. So we're going to send 5 volts out to in1 and 0 to in2. That's great. You put the car in drive, but unless you step on the accelerator pedal, you're not going anywhere. We are just stopped at the red light. Let's get this speed going. And remember, speed is a little bit special because we are not just like turning it on and turning it off. We want to be able to pick a speed. So we're going to use a different function, and that is analog write. This works very similar to digital write, but instead of high and low, we can pick something that we want to pick. So the ENA pin, we're referring to the speed pin. And here we are going to enter in, we're going to enter in a value anywhere from 0 to 255. One could assume 0 means stopped. 255 means max speed, pedal to the metal, lead foot. Let's lead foot this thing. Why 0 to 255? And this is what pulse width modulation does. The digital pins, they can't send analog voltages. So it kind of fakes it. It works with a duty cycle. So with a duty cycle of 0%, it's just sending out 0 volts. And a duty cycle of 100%, it's sending out the 5 volts per time interval. And you can see the vertical green lines. Those are your specific time intervals. So the percentage that the power supply is sending power to the motor kind of determines your duty cycle. So if the motor is getting power 25% of the time, that averages out to 1.25 volts, which also is basically a value of 64 in PWM value. So we're not delivering directly less voltage. We're kind of like fake delivering because the power supply is being turned on for less time per time interval. So theoretically, when I plug this in, nothing is going to happen because there's no code in here unless I left some old code from another project. Well, we're going to find out. You can verify the code and it's going to check it for errors. All of us got to hold our breath here. All right, let's upload it. And if it's verified, it usually uploads without problems. Okay, it's turning counterclockwise. For a lot of the motorized projects, the direction of the motor may not matter. But if it does matter, because maybe you are dropping a spider from the ceiling and then it's got to go back up to the ceiling. So one way to fix it is with the code and just swap your highs and lows. Problem fixed. So if I swap this to low, and I swap this to high, and we're going to upload it, and nothing's happening because I didn't plug it in. Now we see that it's moving in a clockwise direction. So that's usually the easiest way to fix it. The other way to fix this is actually to take these two leads and swap them. Put the yellow or power lead up top and put the ground lead on the bottom. Leave the code the way you had it, and it should work just fine. Back to the code. Why don't we try different speeds? See what happens. Let's move it halfway. When I lift it, it sounds a lot better. It's just the vibration is hitting the table and kind of creating a, like a humming noise. Let's try 50 and upload. All right, so why isn't it moving? It's just making a sound. For every motor, it's going to have its own unique bottom because at some point, the average voltage that it's getting is so low that the motor can't even really function. Figure out what the bottom is on your motor first. So that way you don't write all this code and then realize why is my motor not moving? So we know that our bottom is 70. So we'll use that for our future code. So now we know how to move it in one direction, move it in another direction, and set a speed. That's cool, but that's not really different than kind of what we were doing with the motor controller. We gotta step it up. We have so many tools here. So next, why don't we turn the motor in both directions or one direction and then change to another direction within the same program? This is great for the spider example. If you have the little spider coming from the ceiling, the motor will turn in one direction, stop, and perhaps the spider does some kind of animation, and then the spider will then retract back into the ceiling. It's going to turn in one direction at a speed of 255. Now, how long do we want it to turn in that direction? Because at some point we need to stop it, so it can then go the other direction. So let's keep it going that direction, I don't know, for 3 seconds. 3 seconds. So this is a new function. It's called the delay function. And Arduino will usually read each line and execute it super fast. You won't even be able to see it turn, before moving to the next direction because it happens so fast. So we want to pause it for 3 seconds, and delay takes milliseconds as the value between the parentheses. So 3 seconds is 3,000 milliseconds. Then what do we want to happen? We want it to change direction. Digital write the in one pin low and digital write the into pin high. So we're just basically reversing this situation over here. And how fast do we want it to go? Well, it depends. We can make it as fast or slow as we want. So maybe the spider drops down really fast, scares the people, and then slowly retracts back up. Maybe we'll do a speed of like 175. We can fine tune it. How long do we want it to be going up? Obviously, because it's going up slower, we're going to need to increase the time. But for our demo purposes, why don't we just keep it at 3 seconds as well? This would take some trial and error by mounting your spider. So it's going to come down for 3 seconds, but then we want it to hold that position. So why don't we then stop the motor? So let's do digital write in 1 pin low. And we're also going to digital write the in 2 pin low. And we want the spider to stay stopped for like 2 seconds, 5 seconds. He's got a show to do. So basically what's happening here is he's coming down from the ceiling at a speed of 255. And he's going to take 3 seconds to come down from the ceiling. Then we're going to turn the motors off. Both directions are going to be set to low, so it's not going to turn in any direction. And it's going to sit there for 5 seconds while maybe perhaps some other animations go off of your choosing. Then it's going to reverse and take it back up into the ceiling slower at 175. And it's going to take 3 seconds to do this. Then it'll repeat and come back down. And I guess as a good measure, we should probably pause the motor up at the ceiling as well. So, we'll pause it for maybe 2 seconds before it comes back down and scares people repeatedly. Digital write. Actually, we can just copy and paste right from here. And we know how this goes sometimes. Sometimes it gets all jumbled. So it's just going to repeat this over and over again. Now you can always hook up a motion sensor so it does do nothing until somebody walks by. And so there's a lot of further ways to kind of control this. All right. So it's turning at max speed. It stops. It should turn the other way a little slower. All right. And then it should stop for 2 seconds. And then the spider is scaring people. Oh my gosh. And now it's retracting back to the ceiling and pausing there for a second. So we know now how to turn the motor in each direction within the same program. We've just been setting a single speed, it does something, and then a single speed where it does something else. But what if the motor speeds up on its own? So this could be a zombie crawling at you where it starts slow and then it starts to get fast. And then maybe it starts to get slow again. So let's see if we can change speed. We'll leave the direction alone because by this time we know how to do direction. And we start again. We've been analog writing the speed and putting in a specific number. Well, we want that number to change. So we're going to create another variable up here. So that way we can house a number in this variable that can change. So this is also going to be an integer because it's going to be a whole number. It's either going to be 0 to 255. So we'll call it speed. Super creative, I know. We're actually not going to set it to anything. I'm going to leave it as is because we'll set it later in the code. Sometimes you want something to start at 0 so you can set it here. But no, we just leave the speed alone. So in the loop, how are we going to do this? Well, first we need to figure out a direction, for it. So let's digital write in 1 pin high. And therefore, we're going to write the other one low. Now, in order to increase speed, let's increase by 1 increment at a time. So it'll start at 0, or in our case, 70, because remember, it's not going to start until it starts at 70. So from 70, an increment by 1 all the way to 255. The easiest way to do that is with a for loop. So we started with for, and the initial condition is we want the speed to start at 70. You can put whatever speed is the slowest for your motor, or you can put it at stopped. You know, you can start it where it doesn't even turn, and then it'll increment up and start turning. But we'll start it at 7. So the first thing we specified is, where do you want the speeds to start? Now, how do you want the speed to move? So the speed, or the condition to add 1 to the speed. I'm actually going to use motor speed because I noticed it changed colors. So that might be that it's a keyword for something else. So we don't want to confuse it. So let's do motor speed and motor speed. There. So long as the motor speed is less than or equal to 255, well, we want to increase the speed, right? So motor speed plus plus. So basically, we're setting up a condition. We want the motor speed to start at 70. And so long as when this loops back, the motor speed is still under or equal to 255, we want to keep adding 1. And we do that with this plus plus situation. And all that is shorthand for like speed equals speed plus 1. That's pretty much like what it is. You can see I've started another bracket here because so long as this condition is true, it's going to execute the code inside this bracket here. And what we want it to do, we want it to analog write the speed pin or the ENA pin by the motor speed. And how long do you want the motor to run at each speed? I don't know, let's try 250 and see what happens. So what's happening here is the motor's going to start at 70. It's going to run for 250 milliseconds. Then it's going to come back here and it's like, oh, 70 is still less than or equal to 255. It's less than 255. What do? Add 1 to it. So now it's going to write 71 into motor speed. And that's why we use variables. You can't put a number in here or else it's not going to work. So it's going to hold that for 250. It's going to come back up here and this gets ignored. It only gets looked at the first time. It's going to go here and say, okay, yeah, 71 is still less than 255. What do? Add 1 to it. Now it becomes 72. Hold that for 255 and on until it reaches 255. And then it's going to come up here and say, okay, is it less than or equal to 255? Well, yes, it is. So let's add 1 more. And when it comes back up, it turns into 256. So when it comes back up here, it's going to say, is 256 less than or equal to 255? It's not. So it's going to jump out of this whole thing and it's going to jump into a new thing, which we shall create. Actually, once it reaches max speed, let's keep it going for a little bit. So we can definitely see like a visual cue that it's reached max speed. So let's keep it going for 1 second. Now let's start to decrease the speed. Same deal. We're going to go motor speed. And we're going to start it at 255 because it's going at 255. What's our condition? So our condition is so long as the motor speed is greater than or equal to 70, because that's kind of the slowest that our motor will go, then what happens? We want to take that motor speed and likewise minus from it, right? We're going to start at 255. So long as the speed is above 70, we want to keep bringing it down. So here, now we need to actually specify to analog write the values to the pin. So analog write the ENA pin by the motor speed. Like that. And then we'll keep it the same, so each increment is going to last for 250 milliseconds. So you can, in essence, accelerate up real fast and then accelerate down real slow just by making this number bigger. And then we'll keep rotating it slow for another second. All right, it's starting slow. Slowest acceleration ever. Like granny's behind the wheel, this one. All right, in the code, I'm actually changing these speeds because it's like way too slow for me. So let's upload to new code. All right, so this is moving a little faster. Getting up to that max speed. So the smaller you make this delay within your for loop, the faster it's going to move through those increments. And here it's already slowing down. Now, say you don't want to increment by 1. Maybe you can go motor speed plus 10. That means you're going to increment by increments of 10. So if you start at 70, it's going to add 10 to that, 80, 90, 100. And that should move you much faster through the increments. So I'm going to upload this new one and it should speed up. See how much faster it speeds up because it's going in increments of 10. And now it's slowing down slowly because we didn't change that. So it takes a little bit of experimentation until you get the movement you want. Let's do -10 over here and see. Or you can go in increments of 20 or 50. It could speed up real quick. Now you guys can write kind of a program movement using speed, using motor direction, and you can basically orchestrate something from start to finish. But what if we just kind of randomize stuff? How would we randomize the speed? We've chosen a direction. So let's analog write the ENA pin. And we want a random speed here. And you already saw, that turned a color. So let me give us a little space. There is another function called the random function. And it takes 2 values like that. Set a low and set a high, and I'll pick a number in between. Our low is 70. You could put a lower number where your motor will stop. So it could be doing something, stop, and then do other things at different speeds. I'll keep mine at 70, and I want the max to be 255. Now I'm going to put 256. So why? Because it will go up to this number -1. I used to put 255, and that means that it'll pick a number randomly from 70 to 254, right? So always remember on the high end to add 1. So how do we stick this function in here? Well, quite simply, we're just going to kind of copy and paste, although I'm kind of writing it out like that. So basically, this parentheses here closes this parentheses, and this parentheses here closes that parentheses. And the little semicolon, we just kind of put it after the whole thing. This is going to go through so quickly. It's going to turn a direction, pick a random number, immediately go back up here, pick another random number. So we wanted to pause at that random speed for a certain amount of time. And what do we want it to be before picking another speed? Let's do every half a second so we can kind of get a sense of the speed. So every half a second, it's going to pick another random speed from 70 to 255. Let's upload the new code. See how it's kind of changing directions randomly? Or not directions, it's changing speed randomly. So that starts to give your prop kind of a different unpredictableness to it, which I think makes it look more realistic. Now, of course, we are cycling through random speeds rather quickly. This would probably make your prop look kind of jerky, and so you may want to spend a little more time at your random value. Can we randomize the speed and direction? So you never know what direction and you never know what kind of speed you're going to get. We're going to leave this code as is because we already have the random speed situation going on here. So let's see if we can get the random, kind of like add this into the high and low. I'm going to go ahead and delete him. And we know we need random, right? And we know that we need two values in here. Low and high also corresponds to a 0 and a 1. 0 is the low. That means don't turn it that direction at all. Oh, but we don't want to put 1. We want to put 2 because then it'll choose values 0 through 1. And I put a 1. All right. So, and you'll see that sometimes I have a space, sometimes I don't have a space. Spacing doesn't matter so long as your statement, your complete statement is on the same line. I'm just typing fast, So here we want to do the same thing. We want to randomize 0, 2. So what's going to happen here is that it's going to read this line of code. And for the direction, it's going to pick a 0 or a 1 and pop it in here. Then it's going to go to the next line of code and it's going to pick a 0 or 1. I mean, sometimes you'll end up with 2 zeros. Sometimes you'll end up with 2 1s. Now, what happens when it tries to go in both directions? Oftentimes, the motor driver will act as a brake, so you'll never see it try and go in 2 directions at once. Sometimes we'll get a 1 here and a 0 here, which means it'll turn in one direction and then, the opposite direction. And all while that's happening, it's going to pick a speed. Uploading the new code. Let's see. Okay. Yes, sometimes it gets the 00 or the 11s where it stops. So you can play around with these numbers and kind of see what you get. If you guys get something cool, definitely post it up in the community. I would love to see. The final thing is that it's this time situation. It's always 500 milliseconds or whatever milliseconds that you happen to set it. Well, let's randomize that too. Yeah, random. And the shortest we want it to go is maybe like 250 milliseconds. That's pretty short. And say the longest, let's make it 3 seconds. So 3001, add that 1. And let's see how that works. Oh, it's angry about something. Oh, I forgot a parentheses. There, I gave it a plethora of parentheses now. Let's see what happens. All right, accepted it. That was like a fast one. It picked a high speed for that in a short time. We also have this 3 seconds. So if it happens to choose double zeros where the thing doesn't turn, it's going to stay stopped for 3 seconds. So you can continue to massage this to your will and see kind of how you like it. We've gone through a whole bunch of animations. If you guys use the code, or heck, if you guys come up with your own code, definitely post it in the community. I would love to see what you guys are working on because clearly I just keep adding to my project. So you definitely can't see what I'm working on. These are shot live. So inevitably, there are things I forgot to mention, misspeakings, all that kind of stuff. And I get to the end and I said, oh, I can't believe I forgot to talk about the most important part. So click the link on the bottom. There is a full tutorial where I cover everything that I probably forgot to talk about. Join the community. I would love to see what you guys are working on. We do these live and as well as our live Zoom community builds. It's just time that we dedicate together to push these things along. So have a great night, guys. See you at the next workshop. Bye.